Okay, so let's now go to the industry session. It's really great to have this again. We started this last year, and I was personally one of the people who didn't like the name applied category theory because it had applied in it. While I think a lot of stuff we're seeing here is very foundational science nonetheless. I mean, the completely new paradigms, ideas, methods, totally foundational. On the other hand, if you do true foundational science, you will get impact in the real world, if it's right. And that's what we're going to see here now in the next session. So we get all these industry representatives who are going to tell us what we are doing is useful for them in the real world. So that's great. So if David's schedule still holds. David Spivak?
Yes, I'm here. So I think that I pasted the schedule into chat.
Okay. So
Alan Ransell from Protocol Labs is first.
You just did this. Okay, I see now. Okay, so the first speaker is Alan Ransell from Protocol Labs.
Hi. Let's see, I'll share this. Hi, can you see that? And do you need me to record this locally, or is that handled?
It's handled.
Okay, great, awesome. All right, hi, I'm Alan. I'm a researcher at Protocol Labs. And here are pictures of a few people from the PL community that have had run-ins with the ACT community in a few different capacities. So just wanted to put their pictures up there to kind of make those connections. So I want to say that the title for this talk is more sort of aspirational than declarative, in that Protocol Labs as a company is really focused on building working infrastructure for the decentralized web. And there are a bunch of reasons that I'm going to go into that we think that the decentralized web is going to be a more sort of interesting and richer place to do functional programming and apply category theory than the centralized web that it's replacing. And to sort of add color to that, I'm gonna talk about three different things briefly. So firstly, content addressing, which is the data model for the decentralized web, and IPLD, interplanetary linked data, which is, sorry, content addressing is sort of the addressing basis. IPLD is the data model for the decentralized web. And then the third thing is WebOS, which is this sort of longer term vision for what we want the decentralized web to become. And if you think of these first two, content addressing and IPLD, as being sort of two ingredients for that WebOS vision, we think that category theory is a third necessary ingredient to get there. So firstly, content addressing. So the centralized web and the way sort of the web was designed is all based on location addressing. So in the upper right-hand corner here, all of these different devices connected to the web all have IP addresses. And when you want a piece of content, you say, go there, right? You have the IP address for the content, you link to that IP address, and you sort of cross your fingers and you hope that it's still there. Whereas in the decentralized web, we use content addressing, where instead of an IP address, you have a content identifier, and that is based on the output of a hash function run over whatever piece of content that you're requesting. So both of these images are on the interplanetary file system, which is a big part of the basis for the decentralized web that Protocol Labs built. And if you request a piece of content using a content identifier, you're not saying go there, you're saying I want this, right? And there are a few benefits to this. One is that once the network serves that piece of content to you, you can verify that no one's tampered with it, right? Because part of that CID is this hash function. You can hash the piece of content you got, make sure it's everything you're doing is sort of safe. A second is retrievability. So link rot is a huge problem, right? You say, I want this piece of content that I think is here. If it's not there anymore, you can't really do anything about that. But if you are content addressing all of your content, then you can say, you know, as long as that content is still available on the network somewhere, you can get it. And so, So those are two of the sort of big benefits that are a little more obvious. A little less obvious benefit of content addressing is the sort of radical interoperability between these different data structures, right? So a long time before the decentralized web, people were using Merkle trees to structure their data. So Merkle trees are already based on these hash links, right? So blockchains are Merkle trees. Git, the version control system, is based on Merkle trees. And if you transform from a location addressed system to a content addressed system, with that shift in perspective comes the shift in perspective on those individual projects, right? So when people were building these individual projects, they thought of them as these own separate pieces. But if you use content addressing across the entire decentralized web, all of these individual Merkle trees become part of the same Merkle forest, right? And so this is pretty low level, but you can see how content identification has sort of the flavor of a more semantic version of the web that we'd like to work towards. And we think that's part of the reason that the decentralized web is going to turn out to be a richer place to apply category theory than the centralized web, because it's going to be easier to relate your work to these sort of real world immutable data sets in this global namespace, this global sort of Merkle forest. So a second piece of this is interplanetary linked data, or IPLD. And I'm going to talk in particular about IPLD schemas just briefly. So IPLD schema is an algebraic structural typing system meant to be compatible with the decentralized web. So it allows you to construct types by relating more primitive types algebraically, to serialize data based on those types, to encode and decode data and shard large data sets in a way that you can store them on the decentralized web. And so a few features of IPLD schema that are interesting from sort of a functional programming point of view and sort of a more pure math point of view are the existence of product types, which are structs, and coproduct types, which are sums or unions, as well as optional types, which are an analog of the maybe type in Haskell. And so both IPFS and its sort of content addressing system and IPLD are both out there. So people use them right now. They are sort of a big part of the basis for the decentralized web, and are part of working towards this more sort of semantic web vision that we sometimes call WebOS. And so what we mean by that is that when we think about the future of computing on the web, we wanted to go pretty far beyond what today's apps can do. So as much as possible, we would like a global namespace, not just for data, but for sort of higher level knowledge. And we want this to be radically interoperable as much as possible in the same way that data structures are. So it's pretty clear that the theory to work with higher level knowledge in this radically interoperable way, which involves things like model fusion that we just heard about, the theory to do that in sort of a general way doesn't exist yet. And of all of the different tactics that people have proposed and all of the different approaches to this, we think that the ones proposed in sort of the applied category community, category theory community, make the most sense and are sort of the most promising route to get there. And so we see our role as a company being to help accelerate the transition towards this future by applying a bunch of new ideas, starting with sort of blue sky research, ideas that have the flavor of this sort of more interoperable web that we're going for, and help sort of usher them towards both prototypes and development. And so we have a bunch of ways of collaborating with people. Firstly, there are a bunch of researchers at Protocol Labs, including me, who are working on related projects. So you can see our research website, which I'll have a link on the next slide. Email us. We have RFPs. Those are mainly focused on solving specific questions within the sort of infrastructure that we're building. We have open proposals that are sort of an RFP with no description if you want a grant to work on something that's related that we haven't thought of. And we sponsor events like this one. So please get in touch. I'm really happy to talk to all of you and take some questions.
Thank you. I don't see anybody specifically asking for questions, but I see some comments by Toby, who was also eager to talk before. Toby, you want to say something here?
Hi, no, I wasn't saying anything in particular, just that the content addressing looks a bit like how the brain addresses different ideas. And it's quite nice to see that being realized in our sort of physical computational systems, as well as just the ones we have in biology.
Yeah, definitely. I saw your talk yesterday. It makes a lot of sense.
I also see now a question by John.
What does IPLD do for us simpletons? I mean, so IPLD is sort of how you structure data, right, on the decentralized web. So it's a type system basically, right? So you can build types, check to make sure data structures that you're working with sort of match those types, and then sort of go in both directions, right? So it interoperates between these sort of lower level IPFS-based sort of content addressing systems and sort of higher level systems for building whatever you kind of want to build on top of that.
And oh, there's a lot of questions coming now. So, okay, I think Tim Sears was the first one. That's the last one we're going to do then.
Yeah, I don't actually know what Unison is.
I'll rate you offline on that.
Sure, sounds good.
Okay, there's still a lot of questions, but I think Alan can probably check out what's happening in the online chat box, because there's now like a whole string of questions popping in, including like whether you're looking for customers and things like that. So we'll now go on to the next talk, which is Jelle. Is Jelle somewhere there? Jelle?
I think it's Ryan next.
Yeah, I'm
ready to go.
Okay, that's, oh, Ryan. Ryan
is first.
Is Ryan there?
Yes, I'm here. I just have to share my screen.
Very cyber
now. Can you all see my screen? Can you hear me?
Yep, good.
So yes, so now we have Ryan Wisnesky from Conexus, where, as far as I know, also David Spivak is. Right, David?
Yes, so I can take it away. So, and I'll try to make this quick since these are short talks. My name is Ryan Wisnesky. I come from a company called Connexus AI, and the point of this talk is to tell everyone the who, what, when, where, why, and how of what Connexus AI is, what that means to you here in the Applied Category Theory Conference. So yes, indeed, David Spivak is one of the co-founders of Conexus. He's the mathematician. Myself, I'm the computer scientist. I've met a lot of you here before at the other conferences. Nice to see you all again. Sorry we can't meet up in Boston. Eric Daimler is our business co-founder. And what we're doing is trying to apply all this category theory, and in particular, David's work on functorial data migration to solve problems in the data space. So these are like ETL problems, extract, transform, load problems, data integration problems, IT interoperability problems. And the why we're doing this is simply because other technologies can't solve these problems, right? And so as entrepreneurs and not just academics, we're really here for not only fun, but also profit. But hopefully everyone here shares the philosophy that some of these difficult technical problems can't be attacked except using category theory. So anyway, we're out in Boston right now, but we're out in San Francisco right now. David's still in Boston. We have a team sort of popping up organically in Munich because of the pandemic. I got stuck over there, and then a group of folks down in DC around Sub and Spencer we talked to a lot. So we were grant funded for a while. Now we are seed stage funded, so startup trying to commercialize a tool, which I'll describe at the end of this talk. But anyway, what's the relevance of all this shenanigans to you folks here? So we do maintain an open source project called the CQL project that you can use to do category theory, especially finite category, but some finite categories, but some infinite stuff. We are selling, of course, commercial software that folks can use. Sometimes we hire people, and then we just like to collaborate in general as academics. I think it's mostly David who does that now, but you know, we're working with people at Tinkerpop on some systems aspects and stuff. So with that in mind, let me use the last half of the talk just to give the very briefest overview of what the technology we're building is. So people here may or may not have heard of this categorical data project. For example, it's cited in papers by Evan and some others. The basic insight is that, you know, category theory was designed to migrate theorems from one area of math to another, or maybe not designed with that in mind, but used to that effect. And so one might think that in as much as knowledge is a form of math, that you could use category theory to migrate data from one schema to another. So we've been off pursuing this along the lines of David's work on functorial data migration, and deployed it with a bunch of people, which led to the commercialization pathway that we're on now. So what does this look like? And hopefully this will appear familiar to most people who have been at this conference. In fact, I think we just saw this exact same schema in Julia, but the basic idea is here at the top. You have a finitely presented category, which is to say a directed labeled multi-graph in a set of equivalences, equalities between paths through this graph. So for example, you might have employees that have managers, employees work in departments, departments have secretaries, these things have names, and you have some path equations in your category saying that every manager works in the same department that they manage. So this induces a category, the path category on this graph. A set valued functor can be represented as a set of tables as such. So here's our set of employees, they're 101, 102, 103. Here's the function works in that takes each employee to their department, right? Employee 101 goes to department Q10. And this is the basic idea behind categories being schemas and data as set valued functors. So the technology that we are commercializing at Conexus looks like this. So it's an integrated development environment. It lets you write down finitely presented categories, functors, and about 100 other different kinds of artifacts. But then unlike some of the other systems we've heard about, the focus of this tool is on solving the hard problem of automated reasoning. So the tool looks at what you write, it constructs an automated theorem prover that decides the word problem for the category you wrote down by doing sophisticated analysis, and then it enables you to do all kinds of math on your constructions. And so here's you know, just what the data looks like in the tool. So for example, you can see like the encoding of numbers as terms and stuff like that. So anyway, you know, the details here are not too important, but I do want to mention that, you know, the tool, it's industrial strength, it's ready for people to use it now. There's 100 constructions you can do. It's not general purpose category theory, right? It's designed particularly for ETL type of stuff. So it has very fast algorithms for left and right con extensions, very fast automated theorem provers, but kind of all specialized to a data setting. And that is about that. So I'm Ryan. I've been kind of in and out of the conference. I'll try to hang out on Zulip chat and all that today. David, of course, is great, and he's around a whole bunch. Here are the websites. So categoricaldata.net has dozens and dozens of papers from us and other people. You can get our technology itself at connexus.com. Special announcement, we are introducing a product designed to help users of SQL, the structured query language, by applying some of this automated theorem proving technology to SQL rather than our own language that you saw here. And of course, collaborators, customers, you know, everyone is welcome. So we're here to do outreach, and thank you all for coming. Hopefully we made up a few minutes of time. Happy to take questions now. Thanks again.
Thank you. I see one question from Mohit.
Sure. Oh, how do I find the question?
Well, well, I can say it. I was just curious. Have you come across any applications to non-SQL databases like Amazon DynamoDB, or there are so many out there? Because you also mentioned ETL, so what about things like Hadoop, and does SQL fit in any of these ecosystems as well?
Yes, that's a good question. So we tend to be relational algebra specific, or we lead with that because the connection is so direct with the tabular representation of data. However, category theory is a universal acceptor, right? It's a great meta modeling language. So right now we're working on an RDF OWL importer, for example. We're doing work with the people at Tinkerpop on property graphs. Pretty much any data model you can formalize can be formalized in category theory and then related to other data models. So the answer to your question is yes, and it's actually a key piece of the value proposition. I see another question here on the channel. How does this compare to GraphQL? So interesting question. GraphQL itself is more like a REST API wrapper than a language. But I think the answer to your question is that there's this interesting duality, or duality is probably not the right word, but it's our schemas that are the most graph-like things, right? Our schemas are literally directed graphs with path equalities on top. That's a presentation of a category, whereas our data is tabular. And so ironically, we tend to see the most connections to graph databases through our schemas rather than through our data. But in category theory, you can turn set valued functors into categories with the growth and deconstruction and vice versa. And so we are actually, that's where we're seeing most of our traction commercially, is with people who are manipulating graph data. You know, go figure. Other questions?
Okay, I think we are sort of now out of the 10 minutes again, so we need to move on. Now Jelle. Is Jelle here?
Yeah, I'm here. Let me do the Zoom gymnastics.
Are you able to share your screen?
I think it's working now, yeah.
Great.
So yes, we got now Jelle Herold from Statebox.
Do you see this? Full screen?
Yeah.
Yes. Thank you.
Okay. Crap, no, I lost my clock. Yeah, so I wanted to talk about category theory and my experience of selling it a little bit. And instead of using cats to make this lighter, I'm going to use cars to draw some analogies. So category theory, often people try to set it like this, like a very nice, fast car, or any fancy startup, you want to set it like this, your AI startup. But when you think about industrial strength, and maybe even in terms of industrial revolution, that I think might be possible with category theory, then maybe something like this is a more appropriate type of car. This thing actually exists. But if you were to get a car from us now, if we are your categorical car shop, it looks really a bit more like this. You say, look, this is we found the universal car. And it's maybe a little bit disappointing. But of course, you have all these nice properties of composing cars and so on and so on. So person probably going to ask, well, what's up with this car? Like, did you actually build it? And then we go very proudly, we bring you to the garage and we show you the car. And there it is. This is our car. Our implementation, our first implementation of this universal car. And customer again might be a little bit confused, and he's like, okay, so what's the point? And then you say something like, well, the car doesn't actually need any maintenance or fuel because it never breaks down. It's just the implementation of this universal perfect car. And customer gets, or your investor gets very confused. He goes like, well, how is this possible? This shouldn't be possible. Cars need fuel, they break down. And you pull out the monograph. There we show our progress. We made a theory of wheels. We looked at wheels. Our wheels are type defs, so it's very similar to things we heard before. It's a language to describe types or to put labels on the wires of a wiring diagram. And so extensive theory of wheels. Then we go theory of composition of wheels. And we explain like, well, how 2 wheels make a bike and 4 wheels make a car. All kinds of formulas and details. And at this stage, really you want to go, but look, we can put attachments, and this is where you start losing the investor again, because he goes like, wait, what's up? This is Chinese. So back to your car. This is our car. It's a finite state machine Oracle. It's formally verified code that can tell you whether or not you're constructing the execution path of a state machine correctly. And it's building a wiring diagram, and it's very generic. But you notice it doesn't have steering wheel, and so does investors. They go, look, this thing doesn't have a steering wheel. So enthusiastically, you go like, well, we've been working with Ethereum Foundation, other people on like some crypto stuff, and so we have some theory of steering, starting to look much better now, more like a car. And but the guy goes, yeah, but I need a steering wheel. And you talk a little bit more and you go like, look, we have something else. Like, we've built this other thing. It's just a different approach, but maybe you can find some use for this car that doesn't need fuel and doesn't break down, and just put a bunch of these things in place for the time being. And this is usually when people start seeing, okay, maybe there is something to this strange looking, very simple car. So what's going on, in my opinion, is that, or well, you have areas of mathematics, that's the technology, and you have the industry. So I took here something from Mitsubishi. They work in mining, petrochemistry, all these separate businesses. And in mathematics, we have things like analysis, topology. This thing mentions category theory, number theory. And if you were to put these different areas of life, let's say, on a bike wheel, and have these pie charts represent how much we've developed, let's say, the technology on the one hand, and how much the industry on the other hand has big enough problems to need or understand this technology. Right now, we are a little bit in the lower situation where these things don't match up. And we've spent a lot of time trying to figure out where and where are the good matches, and trying to fill in some of these bumps. And once the wheels are more in balance, we're gonna go to this situation that was put out so nicely by Spencer Briner from NIST. He drew this plot, the cost on one axis and the complexity on the lower axis, and the traditional traditional methods, the cost goes up and up and up as the complexity goes up. And with category theory, the cost is supposed to stay manageable. And so even if your budget is infinite, you're gonna work in this red area only. But there's a new area, this blue area, that's up until now has been inaccessible. These are very complex applications, but still rock solid and across domains. And this is why I think category theory is a similar revolution as things like big data and that kind of stuff. It opens up a new kind of application. And yeah, in order to get there, I wrote down 4 things that I think are very important. So community, because we found it has to be a combination of hackers and mathematicians. The communities cannot be separate. You need this absolute certainty, because if the software somehow breaks down at some point, you're never going to be able to use the scaffolding to build up. So you need verified software. It's going to lead, I think, to deep innovation. So this, because it's so abstract and because it's across domain, we have no idea what kind of things we might discover there. And I think it's also very, very important to have Libre software licenses, because those are the kinds of software that stays around for ages, as we have seen with still being able to use, let's say, LibreOffice to read your Word documents. We call this I call this area of applications hyper applications, similar to hypertext, except how now for whole applications. Composable applications, linked applications, we've heard similar ideas before. And we're going to be putting this on Process.io. Another thing I wanted to mention that we're doing to help this reach the industry is we found that we need to give training to make the category theory more accessible and not too abstract. So this is our training, and yeah, if you're interested, you can always go there. That's what I wanted to say, except for following us and if you have questions.
Thank you, Jelle. So there was a lot of comments on the list, which were kind of very appreciative of your presentation. I don't really see any questions. So what are you concretely working on now?
So our idea is that, let's say the killer app of this kind of stuff is the two-dimensional syntax of monoidal diagrams, and then using algebras to separate the meaning or the interpretation of the diagram from the diagram itself. And the most recent stuff we've been working on is like cryptography things, besides the tools you can see publicly. So our category theory library, IDRIS-CT, and the most recent thing is in discrete log contracts. This is cryptography and trying to categorify that. Very exciting stuff. It's related to blockchains. Yeah. And the game theory things with Jules has been going on still.
Okay. Okay, thank you, Jelle. Again, clap, 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 clap. So we move on now to Steve Huntsman. Steve, are you there?
I am. Thank you for inviting me, and indulge me as I set this up.
So next speaker is Steve Huntsman from BAE.
Okay, so yeah, as Bob said, I'm Steve Huntsman. Thanks to everyone for inviting me to talk. Hopefully I will only ruffle a few feathers. So I'm from BAE Systems. You can see the web address there. It'll be there at the end. So I want to sort of talk about the value proposition, and that's a deliberate pun. So we can talk about elements of that proposition as being sort of things that comprise it. So I'll talk about a few of those. The sort of talk that I'm giving now is sort of, I think, a witness of the proposition, you know, if we're thinking type theoretically, but, you know, pretending to, you know, do type theory stuff. If you want to transport what I'm saying to your own experience, you may or may not have the same experience. So there's the disclaimer. So why are we interested in CT and category theory? We do a lot of system engineering. BAE Systems is a major defense integrator. The part that I work for is a pure R&D shop that does a lot of work for places like DARPA, the service research labs, including what's called fundamental research. So for instance, I'm PI on a fundamental research program right now. That said, we do a lot of things that deal with large scale systems, and those get very complicated, as you can imagine. Something like the F-35 is horribly complex. It's $1 trillion procurement, so it's not going to be simple. So we need new math to start to grapple with those sorts of things and make them less expensive and more reliable and easier to build. And I don't think it's going to be contentious for me to claim that the math involved in this sort of engineering is category theory. And at least my experience has been that there's lots of evidence that category theory can help with sort of small scale problems, and you get a lot of precision. You can, you know, obviously compositionality is nice, that sort of modularity, and you can scale very effectively if the problem is simple. But if you have a complex problem, you know, like building an F-35 or modeling it, it's, you know, totally out of reach. And the sort of ability to have very sort of expressive constructs in category theory sort of implies very elaborate constructions that are not user-friendly. And so the question in my mind is, when are those benefits going to outweigh those limitations? So I think the answer is not too long, but I don't think it's yet. So what have we done? So I'll talk about what I've done. some work on nonlinear dimension reduction, basically extending work of Carlson and Memoli to show that there's an LDR technique called tree preserving embedding that happens to be functorial and enjoys some sort of universal property by sort of extension, let's say. Done some work on protocol reverse engineering. So if you have, say, a packet, a chunk of data that's transmitted over a network, it might contain a few messages, and those could occur in different orders. And so you might want to align those in order to sort of say, what is this protocol doing? And in order to do that, you've got to affect some sort of block permutation on these. So this was actually the first place where I ever saw the word operad, because when I was looking for references on the algebra of these permutations, the book by Markle popped up. And I was like, okay, this is a trivial operad, or almost trivial. Dynamical systems theorists might think of it as a bunch of interval exchange transformations, but that got me thinking of what other sorts of things could you plug stuff into. And so along those lines, we looked at sort of control flow in computer programs, and the sort of natural way to look at these has a couple of monoidal structures, series and parallel, like incobordisms and tankles. But the interesting thing is that if you make this sort of ansatz of a tensor structure, you get some very minor constraints that are totally not obvious. So if you're trying to build a good tool that has this sort of structure, you want that nice category, you have to have some sort of dirtiness in your objects, which I think is a good price to pay. And just apropos of nothing, I'll mention that looking at this suggested a degenerate construction of an omega category, which apparently is well known, but I wasn't aware of it. So it's worth noting that looking at real problems can help you discover things, or in my case at least rediscover them. So as far as what category theory is saying and what we're doing with it, I'll argue that these universal properties and functoriality should inform algorithms. So an example that I'm interested here is that transfer entropy has some nice functorial properties, and this, like entropy has some nice functorial properties. If you look at transfer entropy, it's sort of the mutual information between a actuator now and a sensor in the future. And it has a lot of nice algebraic properties, and unlike something like channel capacity, which a couple of you have been aware of my rants on that, this transfer entropy appears to compose nicely, and so that you can actually get things like linearity popping out of it. So if you have a bunch of agents and you want to say, how do I motivate them in the absence of some specific objective, there's a sort of categorical argument that this is a good thing to do. So another example is that data structures should be objects in nice categories, so not just these flow graphs, but that different representations should be some sort of fiber in a fibered structure. Another is that system architectures or sort of generic frameworks ought to have compositional properties. So we're looking at how sort of operatic thinking, if not operads per se, can coordinate multi-robot systems, how to compose verified code. And in general, the sort of argument that I make internally is that compositionality can really help you make the right choices for system engineering. And a lot of it is the sort of separation of concerns and scales that is enforced by that. So I think the term that we use for that in this community is black boxing. So what can industry do to help everyone present and their community? So I think the first thing is real applications where the categorical perspective can help. We can use tools, we can maybe tweak them, maybe in the future at some point we can produce them. And we can provide slots for for people who are interested and capable to to get a job. Not everyone's going to be on tenure track. So I would also be interested to know how you guys think industry can help the community, because I have a very soda straw sort of view of things. So what can the category theory community do to help industry? Well, the first thing is to actually deal with applications, real ones. and think of their sort of implications for things that people build. And the second is to actually train students for jobs outside of tenure track, right? So if students don't have the capability to program, if they aren't comfortable with engineering sorts of things, it's going to be harder for them outside of academia. And my personal sort of idiosyncratic favorite that may or may not be familiar to some of you from a couple years ago is to produce some sort of engineering NLab. And so there's a paper by Selinger in a volume that Bob edited about 10 years ago that is pretty nice, but an engineer would not be comfortable reading it. So I think that something like that, but with a maybe more applied perspective, could be extremely useful for neophytes and dilettantes, especially people like me. So there's some things that we cannot do to help each other. So I don't know if industry is doing enough for things that we're doing to be wasteful. One thing that we can not do to help you guys is to overpromise, right? So we have to talk about what the value proposition for category theory is, and if we overpromise, then the funding agencies will say, we've tried that, it didn't work. So we need to be careful here, of course. As far as what the category theory community can do that sort of is okay but doesn't help, looking at applications that just come from wherever you happen to look, that's fine. It doesn't really help folks like me. Dressing up results, again, it's fine. Doesn't really give me ammunition or new tools. And so that, at the same time, if you say, oh, I took this result and, and someone like me or a funding person says, well, this looks obvious or trivial, or, like you're using an anvil to crush an ant, that won't go over well. And so you really need to talk about what is relevant and significant in the applications that you're doing. And so just in closing, I want to mention something that is common to folks who do work with DARPA called the Heilmeier Catechism. And it's a sort of series of very simple questions that help you articulate what a research program should do. So whenever you're going to apply anything to anything, I think you should keep this sort of catechism in mind. So a big thing that will be hard for category theorists is to use no jargon without dumbing things down or stripping them of their technical content. That's going to be really hard. The second one of looking at how things are done today is going to force you to make contact with real applications, and then what's new and why will it work. That's an important justification for what you're doing. So all of these questions are useful to answer, and I think anyone trying to do anything applied should keep them in mind. So that's all I have. I'll entertain your questions. So thank you.
Thanks, Steve. So there was a lot of appreciation for the NLab for Engineers suggestion by many people. I don't really see any question. We kind of run out of time, but yeah, especially a lot of enthusiasm for NLab for Engineers. It seems there's a lot of hands willing to contribute to that project. Okay, thanks, Steve. So we now move on to Arquimedes. So
Are you guys there? Okay, sorry, I was muted. My microphone was muted. So okay. Good. So I'll be talking about some of the things that we've been doing on using applied category theory at Siemens, and this is something that we've been doing for a few years, but I think we're still at the stage of trying to understand how we use this tool and apply it to solve problems that we care about. So just a brief introduction, and also to frame the context of my presentation. So Siemens is this company. We've been around for more than 170 years, and we've shaped the industrial revolutions, right? And as you see, first industrial revolution was the steam power, then it came the electricity, when we introduced the assembly line. Then in the 50s, electronics and IT, when we automated. Oh, hold on. Can you see the, never mind. Hopefully you don't see yourselves on the screen, on my screen. The Zoom is obstructing some of the screen, but it doesn't matter. So, and finally we have digitalization, right? Where we're now on the fourth industrial revolution. And I think one of the main points of today's industrial revolution is that many of the products that we design and manufacture today, even the simple ones, think of a garlic press or a toy, are designed digitally. And it's not only the design that needs to be done with engineering tools, right? If you introduce electronics and other components, then more disciplines come together. And all these disciplines really need to interact during the design and engineering phase, but also as we produce it, once the product is being produced by machines, CNC machines or robots. This is another problem, another part of product design that many people don't think about. You need to realize a physical product out of a digital spec. So it's a very long process. For the more the product is more complex, you need more people and teams and time and more tools. And I think this is where things, even though we can do it today, things sometimes start breaking apart because the interoperability between tools is not ideal, right? So this is maybe just a little bit of what we do. I represent Siemens Corporate Technology. We're in our headquarters in Princeton, New Jersey. And I mostly work on the future of automation and a little bit of robotics. And these are the two areas that I know the most. And it's always an interesting exercise for me to map the problems that we have into what we've heard of category theory and trying to bring the two together, see what happens. And remember, we are the R&D, so we are encouraged to do that. So with that in mind, I want to give you a brief overview of what we've been doing with applied category theory. So in 2015, when we first heard of it, and most of us are engineers, we heard of this mathematical branch that could help us with interoperability and compositionality. And we said, well, in manufacturing and design and engineering, a lot of the problems that we have is because of the lack of interoperability and the lack of compositionality. So we started some internal R&D effort, and we soon realized that most of the papers out there in books are very heavy, and they are not easily digestible for engineers. So we decided to bring in, and over the last 3 years, we've invited a few summer interns. In 2017, we started working on functional equivalence in mechatronics. And I guess the motivation here was, as you're building a product, the big question is, engineers tend to do over and over again what they know, right? What they've done, the way they are taught, but are there other alternatives that are functional equivalent that could save us weight, energy, or whatever you care about is. And we did some work there. Again, it was very useful. And this is one of the things that I would like to continue to do, to invite interns who are knowledgeable in category theory, because they explain things to us engineers, and this dialogue, sometimes it creates very interesting tools and applications that otherwise we couldn't have done or would have taken us too long to do. So in 2018, as we learned with these interns what applied category theory could do, we identified a problem, which is a robot program, and I'll be talking briefly about it. And we got this award from the Arm Institute. The Arm Institute is the Advanced Robotics for Manufacturing Institute in the US, and they fund research, applied research, to transition these sort of prototypes that have been demonstrated in the lab into an operational setting with the purpose of helping small and medium enterprises. And here, this is with the University of Maryland, some of the work that we're about to conclude, and I'll be showing a video and an example. And last summer, 2 more interns joined us. We worked on assembly planning, and one of these slides was presented earlier during the keynote. That was great to see. And right now we're about to start a project on decompilation, also trying to apply category theory. So let me explain you a little bit of this project that we're doing. we call it the functional interoperability compiler for robotics. And the problem that we're trying to address is that today, robot programming is very cumbersome. As you can see on the right, let's say you want to open this little sliding door. But if you have 2 different robots in your factory, you really need to write 2 different programs and maintain 2 different programs. And from the engineering side, kind of from robotics literature, there is always this, there has always been this dream that you could define goal-oriented programs that are universal across robots. So here the idea, and this is what we set out to demonstrate, that a goal-oriented program, as you see on the left in the figure, here it just says open the door using gripper. That's a very generic way to describe the what and not the how. Right? Remember, the way we program robots today is describing step-by-step how. But what if we could use goals and set these goal-oriented programs? So where category theory was useful, and also from what we learned with the first batch of interns who came here to Siemens, was that these mappings between really software at the end of the day, right? It's something that category theory can help us with. So you see in the middle, this is a decomposed version of the goal-oriented program on the left, right? We get more detail in terms of what steps does the robot need to make to really open the door. And notice that these operations are robot agnostic, right? So it turns out also that NIST in parallel have been working on what they call the Common Robotics Command Language, the CRCL. Think of it like an intermediate representation for robots. And what we also propose there, sorry, it jumped by itself, but with the CRCL, what we are also using it is as the target language for us to compile these goal-oriented programs. And once we are in CRCL, then we map it to the specific robots. So what you see on the videos, on the right, on the top, we have our universal robots in our lab in Siemens, and in the bottom we have a Baxter robot at the University of Maryland, and both executing the same goal-oriented program, and all the mappings are done automatically. And of course, once we set out the framework to do this, then it's, I would say, straightforward to extend it to more robots, right? If we didn't have this, then we would need to be writing custom mappings from all the way from a goal-oriented programming to the robot. And another example that that we started last summer was this idea that assembly planning, and that's really a headache for many manufacturers, right? As I said, even a garlic press or something very simple, assembling a product is very ad hoc. Every company does it differently, and there is nothing wrong with that, but the way we see it, as we are providing tools for design, for engineering, for simulation, it is much better if we provided this unifying framework where you could do assembly, not in an ad hoc way, but in a I would say in a scalable way, in a universal way. So since we had only 3 months, and this was a project that we started from scratch, we knew the problem, but then we thought, well, maybe Lego is a good way to constrain the problem, because Legos have a very basic, or at least the operation that we're considering for assembly is just snap. Pieces snap to one another, they stack on top of each other. And from here, we also had access to a CAD modeling tools that are not as complex as a CAD tool you would use for designing an airplane or a car. But from here, we are showing that from this CAD model, we can extract these, we call it connectivity graph of the pieces. And here, the goal of this compositional planning framework is to find assembly plans, right? And if you think about it, even a Lego, you can assemble a Lego really any way you want, other than Lego provides you some manuals on how to assemble it just for your enjoyment, but you have freedom on how to put the pieces together. And the way you do it, and what you see on the right, you will see a video of how you're actually constructing a house. If you had access to different number of workers, for example, once you start applying constraints, you need to generate a schedule. So long story short is that this was a very first step to create this framework that would let us reason about assembly planning that interconnects with CAD, with scheduling, with planning and simulation. And we demonstrated this in 3 months. It was a great project, a lot of fun. what we're doing now is taking this framework and really trying to demonstrate it in an industrial setting, meaning more complex CAD environment with more complex simulation tools and so on. So with that, I'll conclude. If there are any questions, I'll take them. And I just wanted to say that it is great. And I just want to also mention that we're using CAD Lab here. And for us, I guess CAD...
We're running a little bit over time.
Okay. All right, good. So I guess I'll stop there.
Yeah, it ended up nicely with the talk we saw just before the session, actually. So that's nice. So the comments can go in the chat and the questions. There are some questions now popping in. We'll move on with the next speaker, Ilyas. You are definitely around. I see you.
Yeah, I'm here.
So the next speaker is Ilyas Khan from Cambridge Quantum Computing.
Hi everyone. I'm just going to get the presentation up and do a screen share. Whilst I'm doing that, I will just say thank you to everybody who is involved with the organization, and particular thanks to David, and also behind the scenes, I think, to Destiny. A lot of these conferences are having to cope with this new modus operandi, and this has worked really well. I'm going to talk about Cambridge Quantum Computing, just on a personal basis. First of all, to say that I've got quite a lot of touch points with the community, been involved with a variety of projects. In fact, it all really got started apart from my interest in category theory. It was started by a passion to try and tackle this thoroughly corrupt system of academic journals that you guys who are in academia have been shackled by. I've sponsored and been involved in quite a number of new journals that are open access, and have worked with Tim Gowers at Cambridge, those of you that have followed his evangelical crusade against corruption. And in your particular area, I'm very pleased and proud to have been able to assist with compositionality. There are actually other touch points as well. I'm very privileged and proud to be contributing in small baby steps to David and Brendan's amazing endeavor at Topos. I know that Brendan's going to be talking about that afterwards. We have industrial usage. We're actually doing stuff with category theory, which I'm going to talk about a little bit. And beyond that, I think we are a reasonable sponsor and employer of academics and people transitioning into industry. And the reason for that, of course, is that I work with Ross Duncan, who's the head of quantum software. Many of you will know Ross. Of course, Bob I work with very closely as well now, Harney and various other names in the industry. So this is a real pleasure to be here. A couple of words. So Bob, with me, you won't have to worry about going over the minutes. I will be absolutely strict on time. We're a firm, we're based in England, we've got a decent outpost in Japan and a growing presence in the United States. We've been around for 6 years. There's just over 100 of us now, very science heavy. We're up at 44 PhDs now with, I think, currently the largest quantum native group of scientists that I'm aware of, which is quite a statement. We're a commercial organization. We have a number of industrial shareholders. GSR is a Japanese company in the specialty chemicals area. Of course, IBM, everybody's aware of. Honeywell, most of you will be aware of. I'm not going to do an advertorial about the firm, but I am going to quickly shift to how we use applied category theory on a daily basis. Before I do that, for those of you that are interested, our mission was originally to try and develop applications and some middleware for quantum computers. We envisaged that the only useful machines would be those that were fully fault tolerant. In the last 2 years, I think there's been a shift and a recognition that actually the current crop of machines, which are NISQ machines, noisy, far from perfect quantum computers, will be useful. And I think the story of this last 6 or 7 months is that there's been a significant acceleration in the capacity of the machines or the quantum processors, I should say, that are being built by a whole wide variety of people. There are, at last count, at least 100 companies around the world that are building these things. And I think on a global basis, quantum computing is a very, very, very significant development. I was watching just a few minutes ago to what the Siemens chap was saying about, you know, Industrial Revolution 4.0. I don't know how to think about quantum computing, but there's really very little doubt that there are few areas of our lives that won't be affected by quantum computing. And the reason I'm so happy is that right at the heart of it is applied category theory. There's not no academic application. This is real stuff, and I'll tell you why in a second. But if you look at the slide at the moment that you have on your screens, on the left-hand bottom corner, sort of southwest as you're looking at it, is something called Ticket. Ticket is a middleware for those of you who are in the classical computer science area, and the beating heart of Ticket is ZX Calculus. And you won't be too surprised at that because, of course, we have Ross Duncan, who was the pioneer. Obviously, most of you, if not all of you who are listening, will be deeply familiar with ZX. I'm aware that this presentation and this video might go out onto the internet. And so for those of you that aren't specialists, ZX is most commonly described as a sort of a rigorous graphical language for reasoning about linear maps between qubits. And in fact, which goes beyond circuit diagrams. I think that's more or less lifted from Wikipedia or something. I actually quite like a different description, which is on the ZX Calculus website, which it says that ZX Calculus splits the atom of quantum logic gates. And here at CQC, we use it as a sort of a tensor network description of quantum mechanics and quantum circuits that provides us with a pretty complete set of rules for judging equivalences. I know that things can't be pretty complete, they either are complete or not, but the fact of the matter is that in our applications, we have proven that this works, and there's empirical evidence. And one of the most amazing things about this year is that large companies that are in the quantum computing space are migrating across to using ZX. I'll say something about that in my last couple of comments. This slide really tries to dumb down, mainly for me, the processes where ZX is useful. This is a sort of a 1 to 5 fool's guide to the development process, but we find that ZX is most helpful in steps 1 and 4. I don't think there's a week that passes that we don't find something new and something interesting that is applied. And what do I mean by that? We have a class-leading global quantum chemistry software package, which is at an enterprise level. We have some of the world's largest organizations as clients, and they don't even know that they're using ZX Calculus to solve problems that in a year or two's time will have a dramatic impact on the world that we inhabit. So for example, carbon sequestration or battery life extension. You know, these are real problems, also in quantum machine learning. And that's a great joy to me to see that this is now just being used and not being talked about. And these are serious applications. There's quite a lot of publication on our website, both direct and indirect, and in collaboration with organizations. However, that's not the only place that we're applying category theory. And I'll finish with an obvious relationship that we have. We're very proud to be working with Bob. Bob and his team based in Oxford. Soon there'll be about 10 of them. There's currently about 5 of them. I think they're household names, at least to those of you in the community. I know that there are presentations that Bob and his colleagues will be making about natural language processing. But again, this is an example of something that we have invested in and supported and are very, very excited about. I don't think that you, Bob, are taking necessarily questions, but if you want to, I'll take them here or I'll hang around for whatever the process is. That's my 8.5 minutes done. Thank you.
Thank you, Ilyas. So yeah, I mean, do people have questions here? I mean, I think the community is quite familiar with a lot of the things we are doing at Cambridge Quantum Computing. Like Ilyas, oh, Ilyas is gone now.
Alex has his hand up.
Ah, Alex.
Hi, Ilyas. Thanks for the overview. I was curious about this 40+ PhD students. Is that students doing joint projects with universities?
Oh no, sorry, I should have been a little bit clearer. Actually, Alex, on my notes before I was talking, and then I decided not to say it, is for the internet audience that's out there that really wants to learn about ZX. The best tool I've used, which I share all the time, is your talk in December to the QNLP, the introduction to ZX. So since you've asked a question, I'm going to embarrass you by plugging you. No, to answer your question, we actually employ full-time 44 PhDs. And these are full-time employees within Cambridge Quantum. We do sponsor students. We have a long and I think a rich history of supporting the category theory community by providing PhD students with direct sponsorships and indirect sponsorships. I think 1 or 2 of my boys are coming to you for a PhD next year, but not just with you. And I should say that I also support the homotopy type theory community in certain ways. And if there are deserving cases of people, I'm much more interested in providing financial support with nothing expected in return. I really don't like this compromising attitude of industry where the first thing they do is ask what they're going to get out of it. I respect it to the extent it needs to be respected. But one of the great things about quantum computing is that we're going to hit reset pretty soon. And one of the resets that we are going to hit is this, I used the word corrupt before, but let's just say unfair system of bias. And I think that we want to ensure that at least in your community, there is an element of giving back. We are benefiting from category theory and we want to give back. So all of you, if you've got any interesting ideas or people that deserve a bit of help, you know, it's not about funding the whole thing every time, but it's all about small things as well. So thank you for giving me the opportunity of mentioning that, Alex.
Great.
Thank you, Ilyas. And we actually, with the next speaker, don't go too far away from you. We go to Brandon Fong from the Topos Institute. To be or already existing. Brandon?
Great. Let me... Is that showing well?
Looks good.
Going through the slides.
Yeah.
Okay, great. So thanks, Bob. Whoops. It's been a wonderful session. It's really lovely to see all the ways that CT is sort of meeting industry in the real world. I am really excited to be able to present a project that David Spivak and I have been working on for almost the better part of 2 years now. And this project is called Topos Institute. So this is the first public presentation about Topos. And while Ryan got through how, what, where, how of Conexus, I thought I'd just focus on the first question: what is Topos Institute? And what I want everyone to take away is the answer that Topos is a new independent nonprofit institute devoted to shaping technology for public benefit by advancing sciences of connection and integration. So what does this mean? I'll break it down beginning from the end, so connection and integration. The world is increasingly interconnected. And the talks at this conference, I think, show much of the promise and the hope of the role of interconnection in understanding the world and shaping technologies and sort of building, I hope, a better future. And so I won't really try and convince you more about the benefits and the strength of the work, incredible work that everyone here is already doing. But I will note that there are also downsides of this increasing interconnection, and they're becoming more and more apparent. So to give 3 examples, this conference was originally intended to be held at MIT in person, but because of our sort of inability to anticipate and analyze the effects of this global pandemic, this sort of interconnection of society and the way that this disease is traveling through it, it sort of interrupted this way, this intention of ours to live our lives in that way. Or second, I know many in this community care a lot about climate change, and indeed, sort of Ilyas just mentioned carbon sequestration. And this, again, I think is a problem of being able to sort of being unable to anticipate and control the effects of a whole lot of local actions leading to undesirable global consequences. And third, I want to mention that while technology like Facebook or Google or Zoom increasingly underpins rich interconnections, rich connections, communications between us, it's also increasingly supported by an apparatus of behavioral analysis and modification that is being directed towards undesirable places, for example, to threaten our democracies and hence individual rights and freedoms. And so this is very much a consequence, I think, of the paradigm in which this technology is being developed. And I think these are big problems, and sort of addressing them will be the work of, dedicated work of many people from many different communities. But as scientists, and certainly we at Topos believe that these are in part problems of connection integration, and understanding at a deep level connection integration can help. And moreover, this is exactly what the work of this community is about. The work of sort of category theory, type theory, programming languages, concurrency, ubiquitous computing is about. And so we feel we have a role to play as Topos by studying, by indeed advancing the sciences of connection integration. So what does that mean? Of course, Topos will conduct research. For example, David gave a talk on polynomial functors and how to sort of understand dynamical systems using them yesterday. And Topos will very much continue work in that vein, in the vein of the work of this entire community. But we all know that advancing science is a matter of more than just research. There's sort of development, there's the building technologies, the dissemination, there's education. And Topos will play a role across the spectrum. So for example, we are funding to support the development of CatLab, which James just talked about. And we'll also undertake education and dissemination projects, not only aimed at the university sector, but also from sort of the general public through high school students and primary school students, through to people that already have passed through the university system, practicing engineers and programmers, making sure that they're sort of aware of and up to date with the sort of latest of the science of connection and integration. And moreover, it's about interaction between these groups. So we'll build community, and Topos means place, and we very much envision Topos as a place for convening and collaboration, not only between different disciplines, as we know that category theory is very powerful and effective for, but also between different parts of society, between academia, industry, and the public at large. And for this reason, it's important to us that Topos really is a physical institute. It is a physical place, and so we're based in Berkeley, California, in this sort of San Francisco Bay Area that's very influential and plugged into technology development at the moment. And so this brings me to technology for public benefit. And I've sort of spoken a bit about the role of sort of technologies of connection, such as Zoom in underpinning society at the moment. And we believe that because this infrastructure, these technologies are likely to be the infrastructure of the future, it's important to us that these belong to the people. And so in addition to sort of research on the scientific side, it's important that there's an understanding also of the social implications, the ethics, the science, technology, and society studies to anticipate the impacts of this technology. And also from Topos at work to inform public dialogue and public policy around the possible consequences of these emerging technologies. And finally, sort of no less important, is the fact that we're a new independent nonprofit institute. So we believe that Topos is a chance to reimagine our institutions for the better and build on sort of the best parts of academia and industrial research settings. So taking the curiosity-driven, the academic freedom of academia, but also the real-world contact of industrial research labs and the sort of drive to make an impact. But beyond this, especially in this time of change, I mean, Ilyas has spoken a bit about sort of the corruption in our academic system. And I think it's a great opportunity to imagine how we can play our part in creating a more diverse, sort of inclusive, equitable academic and sort of research and scientific environment. So for that reason, it's really important to us that we're a not-for-profit, that our incentives are really in line with our values, and we have strong governance structures to ensure that we remain on this path. So sort of to summarize that in a single picture, a bit like a string diagram, we see sort of Topos as engaging with this dialogue with industry and society, and viewing sort of the problems that arise through this lens of fundamental science, of tool building, and of impact and ethics, and producing sort of new tools, these outreach materials and advisory work to make an impact in this way. To move towards conclusion, you might ask who's involved. So there's a scientific team. David Spivak and I are leading the project. We've also had great help from Valeria De Paiva and Evan Patterson. It's not only a scientific project, it's really an institution building project. So we're grateful for the support of people like Ilyas, Ed, and the nonprofit expertise of Patricia Tansky. And we're grateful for a number of funding sources. But I will say that this is really a community project, and these are few names, but we're really also grateful for the support of people like Bob and John Byers and James Fairbanks. And indeed, so moving on to what's next, this is just the start of some communications, and we'll sort of launch, we'll be developing, we have an interim website here, but we'll be launching more information within the next few weeks to months, and really sort of kicking off fundraising and developing our scientific strategy towards our official opening in January 2021, so in 6 months. But finally, I want to emphasize that really this is a community effort, and there'll be more information to come about how Topos will interface with this community and other research communities. But we very much invite you all to be involved, and in the meantime, if you'd just like to reach out to us and share your thoughts, we'd love to hear from you. So here's some contact details. Thanks.
Thanks, Brandon, for this. So there's a bunch of compliments and blah, 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 and everybody says, this is great, this is great, this is great. So yeah, and then I'll say, saying great is not good enough, you have to help. Am I right? Am I right?
Indeed. We'll do this together.
Yes, we're all in it together. So, oh, Toby has a question.
Mm-hmm.
Hi, Brendan. Yeah, I asked the question in the chat, but I guess maybe it wasn't seen. So I'm very on board with this project and this program. But I was wondering, how do you see Topos growing? How do you see people getting actually involved in this community effort? Do you have any sort of formal processes beyond, say, just doing what we're doing, like research and education? Because I completely agree, but so far I don't really understand what we can actually do, what concrete things we can do.
So this is very much in development, and in the first instance, my goal is just to talk to people like you and everyone, and get a sense of what the community can do together. More concretely, we're currently raising funding to sort of, we will have permanent scientific faculty, and as I think Joshua just asked about, we're going to have an extensive visitor program and many sort of conferences, training programs, and so on. So there'll be a lot of sort of physical sort of interaction to do research together. In terms of, let's see, yeah, what I think to do now is that we should just continue the discussion about what an organization like this can do, sort of laid out our values. We're developing our scientific research strategy, but it needs to be informed by the collective.
Yes, thanks, Brendan. Because I've been speaking to lots of different people about this kind of community building, and there seems to be a lot of people thinking along similar lines. I guess it's just about connecting them and seeing what happens.
Okay, I think we are now a little bit over time, so let's move on to the next talk, and we can chat about all of this and continue to chat about Topos and all the community things like both Brandon and Ilyas talked about in the pub session after the last talk of this session. And this last talk is by Alberto Speranzon from Honeywell. Alberto?
Yep, ready here. All right, so yeah, thanks a lot for the opportunity to talk. And so I'm from Honeywell, the aerospace side, the R&D lab. And yeah, I wanted to, I mean, some of the things I will say will resonate a lot with what other people have already said, maybe a slightly different point of view. So, you know, when we look at the big challenges in industry and, you know, even beyond, you know, is this idea of being able to understand large system of systems. And, you know, just to summarize what it comprises of, just so that everybody's on the same page, is really highly heterogeneous, right? A lot of system and components that are using very different technologies. It's very large scale, many thousands of fairly complex subsystems, right? And the biggest problem that we face is really this emergent behavior. We can analyze subsystems potentially fairly well, but we don't fully understand how to compose them well, right? And especially we don't know how to analyze them well enough. And so this leads to completely, you know, even in aerospace, you see still sometimes issues occurring with airplanes needed to be grounded because of the, you know, design flaws. So yeah, so the kind of system that they typically I'm concerned with are, you know, aircrafts and their evolution towards what you probably hear now with air taxis and more of sort of autonomy capability on these systems. But if you look at them, they're really complex system of systems, and aerospace is a highly regulated industry, right? You cannot just develop something and hope it will work. You need to be sure it will work. And there is a lot that really goes into that. In fact, if you look at the pace at which new aircraft are built is extremely low. It takes, you know, decades to come up with a new design. And if you look at the new design, is that not very new, just because of the complexities on, you know, be sure that this system is actually safe. And so, you know, when you start looking at these problems, of course, the first things that we do as engineers is the modeling. This could be a modeling of a already existing system or of a, you know, process that we're interested to control. And so, you know, we have seen a lot of people talking about, you know, Petri nets, you know, final state automata, you know, open dynamical system, and so on. But as an engineer, I'm not just interested about modeling. Really, the model is created for the ultimate goal, which is design and analysis. Engineering really requires us to close loops and act on the system and the environment to do something. So the model really is tailored for what kind of analysis and design we can really do. And so, you know, I didn't know much about, actually didn't even know what category theory was until a couple of years ago when I started to work with David and Brendan and Patrick. And I think that the project that we had on the NASA, funded by NASA, was really nice because we touched upon these two different problems, really, because from an engineering perspective, I was pushing on that side, and David and Patrick and Brendan was very keen to see how we could do that. And so at the very beginning, we started right with just the modeling side and all the work that David and Christine and Patrick and Brendan have done on the interval shift to try to model dynamical systems over time interval, and then, you know, building, you know, compose this into systems and getting into something that we call abstract machines. But when we arrive to this point, you know, from an aerospace perspective, I just don't want to be able to model the system. I want to be able to know if the system will satisfy certain requirements. And requirements are just allowed behaviors over intervals, so they're sheaves. But, well, it's not that easy to transform these requirements or contract into a sheaf and then try to understand how this contract, you know, match with what the system input up to behavior of the system is. And so that really led to this idea that we need analysis, right? We need some tools, some methods that enable us to do this checking if these systems does satisfy certain properties. And so this led to the big work that David and Patrick have done on temporal type theory, which then, from the engineering side, from my side, was more try to apply to specific applications that led, to this very nice way of translating something at this level, just modeling, to something that we can do analysis on. And what is nice is that actually you can create a very concrete story that we can tell to an engineer. Why would I need to know what a sheaf is? Why would I need to know what temporal type theory is? Well, there is a story that we can make about what is the benefit when you try to design and analyze the system. It's not just, modeling and analyze the system. It's not just the modeling. It enables you to do actually analysis. And so there is a couple of papers there which tell the story that you find in David's more technical paper from the engineering side, really tailored to be more ground to earth and possibly readable by engineers. So the bottom line is that I think that the success of category theory is if we are able to combine perspective from modeling towards design and analysis. One thing that whenever I present the work that we've done with David, at the very beginning we were having mostly modeling, ideas, and it was very difficult for people to understand why should I bother to learn what a sheaf is or a monoidal category if at the end of the day, I cannot do any analysis. At that point, it becomes a beautiful model, but it's not useful to me to really create this closed loop, right? And be able to control system and say something about them. And of course, the ultimate goal is to be able to translate the design into something that is computational, right? And so be able to write program. So I think there is, as I work with David and we've been touching upon some of these challenges, I got to learn a lot about other things, right? Like type theory and categorical logic and functional programming. So my hope is that there is an opportunity here to bring engineering in some sense within this kind of connected fields, which are today quite separate from engineering, more together, using this sort of loop here as a template to develop something that is mathematical sound. It can be analyzed using logic. It can be implemented using functional programming, and it solves engineering problem. And so this was sort of saying my experience on working with David and others, but really touching upon this loop. So if you guys want to get in touch or you have comment, and the opportunity here is to have a discussion, but we are a bit out of time, so feel free to reach out if you have thoughts. And I like the idea of an lab for engineering, as Steve mentioned, where we could take this few snippets of application and start showing to people what are the templates, what are the patterns that are useful to start modeling and then design and analyze these systems, so that people can understand the benefit of the framework. And of course, one thing that I would like to underline, I am a completely, to make this possible, you cannot just push this problem to the applied category theory community. It's not just you that you need to figure out how to do this. It really requires engineers to become uncomfortable and speak more the language of category theorists. And that's what I've been trying to do. I've been spending a lot of time trying to catch up on category theory. And obviously, it's appreciate that people like David and Brendan are willing to listen and engineer explaining very concrete problems that maybe are mathematically not super interesting, but then as things get together, there is quite some interesting aspects there to be researched. So with that, without taking a lot more time.
Thank you again. So I think there's a question here from Brian. Do you have Brian somewhere? kijken, hè.
Yeah, I think it was more a comment than a question.
Yeah, I was mostly just saying, like, I love this idea. I didn't realize that I was supposed to unmute and say that, but thanks. Great chat. Really appreciate the idea, so thanks.
Yeah, so there is a number of appreciation. So I think this concludes this session. I think it was amazing. It was much richer than last year. I think last year was a small subset of what we got this year. So everything is growing, that's good.